Well, it looks like we're ready to look into directional derivatives, your final tool of Physics 101. So let's use some Physics 101 magic to get there. Yeah, still working. Now in section 10.3 in your lecture notes, so you can check it, this is where we actually introduce directional derivatives. And so far, and I've used the ukulele to demonstrate partial derivatives, which I'm pretty sure is the first time it was done in the world ever. And if we come back to the ukulele and think about partial derivatives, I told you that we can think about different directions within the ukulele. For example, this one, and let's say that when we're going along this direction, we're fixing the y-axis, and in this case, we're fixing the x-axis. And partial derivatives are all about looking at how surfaces were changing along a specific direction. In this case, we would not be moving along this direction, and we would just take this path. And if we do this, then we're traveling along this direction, but we're not moving in this way. This is very limitative, because what if, for some reason, we want to look at the variation of the surface of the ukulele along some curved path? Or maybe we want to go here and then we want to take a turn for some reason. We can do this if we know how to determine directional derivatives, which is what we're going to try to do. One of the problems is that there are so many ways that you can move along a surface. If you're not keeping x fixed and you are varying y, how are x and y varying? Are they varying at the same rate? Is x varying twice as fast? Maybe x is varying to negative values and y is varying to positive values. How do we define all of this? That is one of the major questions that we need to address, which is question 1. How do we define the direction? We need a very specific way to convey the direction in which we're calculating the directional derivative. And obviously, perhaps even more important, but this is a follow-up question, how do we calculate them? And these are obviously directional derivatives. These are the two main questions that we're now going to address. We need to start with question 1. How do we define the direction in which we're taking a directional derivative? And it turns out that the best way to do this is by using vectors. To start off with, let's say that both x and y are increasing. You're moving along a direction for which both x and y are increasing. But let's say that for x, you're increasing it twice as fast as for y. If you think about vectors, and there's many ways you can write them, such as this, and in LaTeX sometimes it is also in bold. Any notation will do, provided you're consistent. If you use a vector and you're trying to convey this direction, that x is increasing twice as fast as y, maybe you could write this vector as 2, 1. The problem is there's many ways you can convey exactly the same thing. A vector that has components for 2 is also telling you that x is increasing twice as fast as y. But you can also think of other combinations. For example, 1 over 5, 1 over 10 is also conveying the fact that x is increasing twice as fast. In order to make it very objective, so that there's only one way to do this, and so we can actually then use it to calculate directional derivatives, what we're going to be using is not just any vector, but it is the unit vector, which we'll denote as u, or like this. This is my u. And just to make it clearer, I definitely don't write it with that exacerbated end, but it will look like this. If you have a general vector, say a vector with those components 2, 1, how do you convert this into a unit vector? It is relatively straightforward. What you need to do is you take your initial vector and you divide by its magnitude or modulus. How do you calculate this? It's relatively straightforward. You get the square root of the square of each component, 2 squared plus 1 squared, in this case, square root of 5. So what will we use to calculate the directional derivative along a path where x is increasing twice as fast as y? We'll use the unit vector. And the unit vector is the same for whatever vector you have here. And this will be given by u equals, and we're looking at the components. That would be 2 over square root of 5, 1 over square root of 5. This will be our unit vector. Obviously, this is the case when you have x and y. If you have a case of a function where the function is defined and has 3 variables such as x, y, z, then the unit vector will obviously be calculated by the same way, but now you're looking at the components of v and then you're dividing by some a squared, b squared, c squared. And the same thing would go if you keep going up in dimensions. Directional derivatives can actually be extended to n number of dimensions, always using the unit vector. And the unit vector is always calculated by dividing a vector that gives you the direction in which you're going by its modulus. And this is the answer to question 1. How do we define the direction for directional derivatives? The answer is we calculate the unit vector. Typically, we are either given a general vector or some direction, and therefore the first step will always be to find what unit vector conveys this direction. And typically, it means we're dividing the components of any general vector by its modulus or magnitude to get the unit vector. And these are the components, in this case a and b, that we would use for directional derivatives. If you go to higher dimensions, you'll just keep adding components. A, B, C, could be D, E, F. So we can move on to section 10.4 with a little bit of magic. But for that, let's meet in the next video so you can have a little break.